Welcome to the deep dive. Today, we're plunging into, well, the fascinating and, let's be honest, often frustrating world of debugging modern digital hardware. I mean, imagine pouring countless hours into designing something incredibly intricate, maybe a multi-million gate FPGA or a complex system on chip. It's designed perfectly in theory, right? Simulates beautifully. But then you put it on a physical board, and suddenly these subtle, elusive bugs appear. How on earth do you find them when you just can't physically see what's going on inside? It's like trying to find a ghost in a machine, the size of a postage stamp. Our mission today is to pull back the curtain on AMD Vivado Chipscope. It's this powerful suite of tools purpose-built to tackle exactly this problem. We're going to explore why our traditional methods, well, they kind of fall short now, how Chipscope works, its magic, its most advanced features, and ultimately how you can leverage it to become maybe a hardware debugging wizard yourself. Let's unravel this mystery.
It's true. The bedrock of hardware design is always verification, making sure a system works exactly as intended before it ever goes into production. But the game has just changed dramatically. This relentless progression of semiconductor tech, huge FPGAs, complex SoCs. It's pushed traditional verification methods, frankly, to their limits.
So simulation isn't enough anymore.
Well, take simulation. It's absolutely our first line of defense. It lets designers test their RTL code in a controlled, virtual world with, complete visibility. It's excellent for catching functional errors, logic bugs early on.
Okay.
But its main limitation, it's completely detached from real-world operating conditions. So many hardware issues just, poof, appear only when the full system is running live on the target board.
Right, the stuff you can't predict.
Exactly. Simulation just struggles to model things like board-level effects, signal integrity problems, power supply noise, subtle impedance mismatches on the PCB itself. It also can't perfectly capture how external peripherals really behave. Maybe the timing deviates slightly from the datasheet for memory or sensors.
Okay, that makes sense.
And asynchronous events, those unpredictable timings, incredibly hard to replicate exhaustively in simulation. And forget trying to simulate billions of clock cycles to find those really rare performance bottlenecks or intermittent glitches. Computationally, it's often just prohibitive.
So what this really boils down to is simulation verifies the code, yeah. But validating the implemented hardware in a real system, that needs something totally different.
Precisely. And the complexity of SOCs, integrating processors, programmable logic, tons of IP blocks, it just widens that gap even further.
Okay, so simulation has limits. What about just, sticking probes on the board like the old days?
The challenge of physical probing. Yeah, before on-chip debug, engineers used external logic analyzers, oscilloscopes, routing internal signals out to unused I/O pins.
Right.
But that's largely impractical for modern devices, these high-performance FPGAs. They use ball grid array packages, BGAs, with thousands of pins. Many are just completely inaccessible under the chip.
Yeah, good luck getting a probe on those.
Exactly. Routing hundreds of internal debug signals to the few available I/O pins, not feasible. And it's incredibly intrusive.
How so?
Well, adding all that extra debug routing, it can actually alter the physical implementation. It changes timing characteristics.
Oh, right.
This observer effect can genuinely mask the bug you're hunting for, or worse, create new timing failures.
Wow.
Plus, external probing itself can introduce its own signal integrity headaches. It's a real double-edged sword.
Okay, so that's out. What else?
And finally, you've got the rise of the SO. Think AMD Zinc Versal families. They seamlessly integrate multi-core processors right alongside the programmable logic. What's crucial here is that bugs often happen right at this hardware-software boundary. Maybe a software driver configures a hardware register wrong, or the hardware fails to signal the software correctly.
The interface problem.
Exactly. And this just screams for a tool that provides correlated visibility into both the hardware and software domains at the same time.
Okay, so we've got simulation limits, physical probing is mostly a non-starter, and SoC integration adds this whole other layer of pain. This definitely creates a massive need for tools like AMD Vivado Chipscope, right? Engineered for deep, non-intrusive visibility at full speed. And I bet for anyone who spent nights chasing phantom hardware bugs, this next part, this is where the magic happens.
That really is the core idea behind on-chip logic analysis. You're effectively synthesizing a logic analyzer directly inside the FPGA fabric. Think of it like a soft logic analyzer.
Okay.
The fundamental principle is instrumentation. This means inserting a pre-designed, customizable IP core that logic analyzer directly into your design's netlist. It gets synthesized along with your design, becomes an integral part of the final bit stream, and because it's inside, it can access any internal signal, No external connections needed for that.
Clever.
And to ensure accuracy, this on-chip analyzer operates synchronously with the logic it's watching. It's connected to the same clock domain, sample signals on each active clock edge. That guarantees precise timing accuracy, which is just paramount for digital debugging.
Right. You need to know when things happen.
Absolutely. Now, to manage the, well, potentially vast amount of data, these analyzers use dedicated on-chip memory, usually FPGA block RAM or BRAM. This acts as a trace buffer. The buffer size, we call it data depth, determines how many clock cycles of data you can capture.
Okay.
And there's a direct trade-off. More depth means more visibility back in time, but it consumes more of that precious BRAM.
So you have to choose carefully.
You absolutely do. It's a fundamental design decision. You're constantly balancing visibility against resources. It's a strategic trade-off.
Makes sense. You can't just capture everything forever.
Right. Continuously filling that buffer would be incredibly inefficient anyway. So the key is a sophisticated triggering mechanism. The designer configures a trigger condition. Could be simple, like a signal changing, or a complex Boolean equation involving multiple signals. The analyzer then only starts storing data when that specific condition is met. And you can position the trigger, capture data before the event, after it, or centered around it. So you see not just the bug, but crucially, what led up to it.
That's powerful, seeing the cause, not just the symptom.
Exactly. And finally, when data is captured, you need to get it out. There's a dedicated communication channel connecting the on-chip debug IP back to a host computer running the analysis software, like the AMD Vivado hardware manager. Historically, this often used the JTAG port.
Right, the standard debug port. Okay, so let me recap. You basically build a logic analyzer into your chip, synchronize it to the design clock, buffer the data in on-chip RAM, and use smart triggers to capture only the interesting stuff.
Exactly.
Then pull that data out through a dedicated channel. That's the core idea.
That's the core idea. These principles give us this amazing window into a running chip.
That sounds incredibly powerful. But it also feels like it could add a lot of complexity to the design flow itself. What's the biggest hurdle engineers hit when they first try using these?
That's a great question. And it leads us right into the Chipscope toolkit itself. Because Vivado Chipscope isn't just one thing. It's really a whole ecosystem of interconnected IP cores and software. The foundational workhorse, the one most people start with, is the Integrated Logic Analyzer, or ILA.
Okay.
It's a fully customizable synchronous logic analyzer synthesized right into the FPGA fabric. Its whole purpose is monitoring internal signals, triggering on events, capturing data at system speeds. You can customize things like probe width and count monitor hundreds of signals if you need to. Data depth setting, how much BRAM it uses, determining samples per trigger, could be hundreds, could be thousands.
Right, that trade-off again.
Yep. And its trigger capabilities.
Right.
They range from simple level or edge detection up to really complex multi-level sequences using Boolean equations. And it has this cool advanced feature called storage qualification.
Storage qualification.
Yeah, it lets you tell the ILA to only store data when some other condition is met. For example, only capture AXI write transactions if the Debugging signal's a high.
Ah, so you don't waste buffer space on idle cycles or irrelevant stuff?
Precisely. It's super efficient for capturing sparse events without filling up your buffer instantly.
Nice. What else is in the toolkit?
Then there's the system ILA. Think of it as an enhanced ILA, specifically built for system-level and protocol-aware debugging. Its big advantage is native awareness of common bus protocols, especially AXI4 and AXI4 stream.
Okay, so it understands AXI.
Exactly. Its value is immense because it automatically groups and presents bus signals at a higher level of abstraction. Instead of raw bits, you see things like AXI write transaction to address 0 by 400000.
That's much easier to understand than just ones and zeros.
Way easier. Invaluable for debugging complex interconnects. You're debugging the protocol, not just the signals.
Got it. What about interacting with the chip?
For that, we have virtual input-output, or VIO. This gives you interactive, real-time control and monitoring of internal FPGA signals without needing to resynthesize the design.
No resynthesis. How?
It functions like virtual switches, buttons, and LEDs right there in the Vivado Hardware Manager GUI. You can use its output probes to, say, toggle a reset line, enable a clock, or inject some data live just to see what happens. Great for what-if analysis.
Ah, okay.
And its input probes let you display the real-time state of internal status signals or counters with very low overhead. Super handy for quick checks.
Okay, so let me try to visualize this. The VIO is kind of like having a virtual multimeter and switch panel on the chip.
Good analogy, yeah.
The standard ILA is your powerful general-purpose logic analyzer.
Right, the workhorse.
And the system ILA is like having a sophisticated bus protocol analyzer built in.
Exactly. A smart engineer picks the right tool for the specific job at hand.
Makes sense. Are there other specialized ones?
There are. Briefly, there's the IBERT Integrated Bit Error Ratio Tester. That's specifically for tuning high-speed serial transceivers, measuring link quality. And there's a JTAG2XI master. This lets you generate XI transactions directly from Vivado over the JTAG cable. Really powerful for testing XI slave peripherals if you don't have a processor running yet.
Okay, quite an arsenal. But all these powerful cores, they need a way to talk back to the host computer, right? You mentioned a communication channel.
Absolutely.
Yeah.
And there's a dedicated communication fabric handling that. It's just as sophisticated, really.
So how does that work?
This is handled by the Debug Hub. It used to be called Icon, if people remember that name. It basically acts as the central nervous system for all the on-chip debug stuff. It arbitrates access if you have multiple debug cores, like multiple ILAs, and it manages the data flow back to the host.
Okay, the traffic controller?
Kinda, yeah. And the architecture of this communication path has actually evolved quite significantly over time.
Oh, how so?
Well, in the pre-Versal era, so 7 Series FPGAs, ultra-scale plus communication was mostly based on the device's standard JTAG port, i.e. 1149.1. The Debug Hub connected to a boundary scan primitive, a B-scan, and the Vivado hardware manager sent low-level JTAG sequences over the programming cable.
Right, standard JTAG stuff.
It worked, but JTAG is relatively slow, especially for pulling large trace buffers back. So with the Versal Adaptive SOAK era, there was a fundamental redesign. On-chip debug on Versal is now strictly AXI-based.
AXI-based. Why the change?
The rationale is pretty simple. Versal devices are these incredibly integrated, heterogeneous platforms, right? You've got the programmable logic, PL, the processing system, PS, with ARM cores, AI engines, AIE, all connected by a super high bandwidth network on chip, the NoV.
Okay.
A slow JTAG chain trying to pull debug data across all that, it would have been a massive bottleneck.
Right. Too slow for the architecture.
Exactly. AXI-based debug offers much higher bandwidth for reading those trace buffers back. It also gives you a more unified debug methodology across the PS and the PL, and it provides far better support for remote debugging scenarios. Versal uses an AXI debug hub that connects directly into the system's main AXI infrastructure.
That's a big shift. So how does this AXI approach affect things like remote debugging if you can't physically plug in a cable?
That brings us perfectly to the Xilinx Virtual Cable, or XCC. This is designed specifically to address the challenges of debugging hardware where you don't have direct physical JTAG access. Think cloud data centers running FPGAs or remote embedded systems out in the field.
Okay.
XVC is basically a protocol that tunnels JTAG commands, or now AXI debug commands, over an IP network, Ethernet, PCI Express, whatever.
So it's like JTAG over IP.
Essentially, yes. It works by having a lightweight server running on the target system, something that has access to the FPGA's debug interface. This server listens for XVC commands coming over the network. The remote Vivado hardware manager then sends commands to this server, just as if it were talking to a physical programming cable plugged directly into the FPGA.
Clever. It decouples the debug software from the physical connection.
Precisely. It opens up a whole world of remote debugging possibilities. Huge for cloud and embedded.
Okay, so we know what Chipscope can do. We know how it communicates. But here's the practical question for engineers listening. How do you actually get this debug logic into your design? It sounds like there must be different ways, maybe with different trade-offs.
You're absolutely right. There are 4 main ways, or instrumentation flows, to get debug cores into your design. Each has pros and cons. Method 1 is HTL instantiation. Some call it IP plug-and-play or RTL insertion. This is the most direct way. You literally go into the Vivado IP catalog, select and customize a debug core like an ILA, and then instantiate it directly in your Verilog or VHDL source code, just like any other component.
Okay, so you write it into your code.
Exactly. The advantage is maximum control. It's explicit, it's visible in your source, it gets version controlled with your design, you know exactly which RTL signals you're probing, often preferred if you want permanent diagnostic features built in.
Makes sense. Disadvantage.
It's intrusive. You have to modify your functional HDL source files, and you need to know exactly which signals you want to probe right from the start.
Right. What's the next method?
Method 2 is probably the most commonly used for general-purpose debugging. Netlist insertion, or post-synthesis insertion. Yeah. The workflow here is, first you synthesize your unmodified RTL design, Just run synthesis as normal. After synthesis, you then mark specific nets in the synthesized netlist for debugging. You can do this in the Vivado IDE, maybe by adding an attribute like mark debug true in your RTL beforehand. Or you can just graphically select nets in the schematic viewer after synthesis. Then you run the setup debug wizard, and Vivado automatically creates and inserts the necessary debug cores, connecting them to the nets you marked.
Ah, so you don't touch the original source code.
Exactly. That's the big advantage. It's non-intrusive to your source. And it allows for more flexible exploratory debugging because you decide what to probe after you can see the synthesized structure.
Sounds ideal. Any downsides?
Well, synthesis can sometimes optimize away signals you wanted to probe or rename them in ways that aren't obvious. You might need to use attributes like keep true to prevent optimization. And sometimes working with those post-synthesis net names can be a bit less intuitive than your original RTL signal names.
Okay, manageable though. What's method 3?
Method 3 is the IP integrator flow. This is streamlined specifically for designs built using Vivado's graphical block design tool, IP Integrator. If you're using IPI, you can simply right-click on any wire or interface in your block design and select Mark Debug.
Oh, nice.
Then during synthesis, Vivado automatically infers and inserts the right debug cores. This is especially powerful for AXI interfaces. It can automatically instantiate a system ILA for you, all configured.
That sounds like the way to go for SOC designs using block diagrams.
It's definitely the most natural and efficient method for those kinds of designs.
Okay, and the last one, method 4.
The fourth one is the engineering change order EcoFlow. This is a really specialized post-implementation technique designed for extremely rapid debug iterations.
Post-implementation, so after place and route.
Yes. It allows you to modify debug probe connections after the design has been fully placed and routed. For example, you might have an ILA already in the design, and you realize you need to probe a different signal nearby. The EcoFlow lets you change just that one probe connection without rerunning full implementation.
Wow, how fast is that?
Potentially minutes instead of hours.
Yeah.
Its big advantage is the fastest possible iteration time for minor debug changes, because it preserves almost all the existing timing-closed implementation. Ideal when you've localized a bug and just need to tweak the probe slightly.
What's the catch?
It's limited in scope. You can't add entirely new debug cores or change things like the data depth of an existing ILA. And crucially, the new signal you want to probe must be physically routable to the existing ILA's location on the chip. It can't work miracles.
Got it. Specialized but powerful for quick turns. It really sounds like efficiency is a huge driver here. Productive hardware debug seems all about the speed of that debug turn, right? Minimizing the time between seeing a problem and getting new data.
Absolutely. Speed is everything when you're chasing a bug. And Vivado offers powerful features beyond just the EcoFlow to accelerate this cycle. A big one is the broader incremental compile flows. When you change your debug configuration, maybe add a new ILA or change its depth, a full design rebuild from scratch can take hours.
Yeah, painful.
The incremental flow is smarter. It analyzes what changed and intelligently reuses placement and routing data from the previous run. It performs synthesis, placement, and routing only on the new or modified logic, basically. Just the debug cores and their immediate connections.
Ah, so it only rebuilds the changed parts.
Exactly. This is critical for maintaining high productivity during that iterative bug hunting process. Saves enormous amounts of time.
What about automation? Can you script this stuff?
Oh, absolutely. That's another crucial accelerator. Scripting and automation with TCL. The entire Vivado design flow, every single step, is controllable through a TCL scripting interface.
TCL, tool command language.
Yep. Every click you make in the GUI corresponds to a TCL command running underneath. This means you can write powerful scripts to automate the entire debug workflow. Project creation, adding source files, inserting and configuring ILAs or VIOs, running implementation, programming the device, even setting triggers and capturing data.
Wow, fully automated debug.
It's fundamental for creating reproducible version control debug setups, essential for team environments or complex regression testing.
Okay, TCL is powerful. Anything newer on the automation front?
Yes. And this is where things get really interesting, especially for Versal. It's the Chipscope Python API.
Chipscope, Python for hardware debug.
Exactly. This represents a major leap forward. It's all about aligning hardware debug with modern software development and DevOps practices. Chipscope exposes all that on-chip debug core functionality controlling ILAs, VIOs, reading data through a high-level, object-oriented Python interface.
Okay, what are the advantages of using Python here?
Several big ones. First, IDE-less operation. Your Python scripts can run from any standard Python environment. You don't need the full Vivado Design Suite IDE installed just to interact with the debug cores on the hardware. It has a small installation footprint, making it perfect for lightweight test servers or embedding into automated regression frameworks.
Makes sense.
Second, extensibility and the Python ecosystem. This unlocks the entire universe of Python libraries for scientific computing and data analysis. You can capture trace data directly into a Python script and then immediately pass it to NumPy for complex analysis, or use matplotlib for custom plots and visualizations.
Wow, okay, that opens up a lot of possibilities beyond just looking at waveforms.
Huge possibilities. And third, it enables truly flexible and customizable flows. Hardware and software engineers can create fully customized automated validation scripts tailored to their specific needs. Imagine a continuous integration pipeline that automatically programs the hardware, sets up complex trigger conditions, runs system tests, captures trace data on failure, analyzes that data with Python, and flags failures all without any human intervention.
That's genuinely fascinating. This progression from clicking buttons in a GUI to TCL scripting and now a full Python API. It really feels like a fundamental change in the skill set needed for hardware validation.
It absolutely is.
It's no longer just about understanding logic gates. It's about embracing software engineering principles, version control, automation, data analysis, maybe even DevOps to tackle hardware complexity at scale. That's a massive shift, isn't it?
It's a huge shift, and it's necessary given the complexity we're dealing with now.
Okay, so you've used these tools, you've automated the process, you've captured the data, and now what? Getting the data is one thing, but making sense of it is the real challenge, right?
Exactly. Capturing data is just the first step. The true challenge lies in capturing the right data and then efficiently analyzing it to find the root cause. First off, mastering those trigger and capture controls we talked about is essential. Basic triggering is simple logic levels, transitions, bus values. But remember storage qualification. That advanced feature where the ILA only stores a sample when a specific condition is met, like W valid equals 1 on an AXI bus.
Right, saving buffer space for sparse events.
It's crucial for using that limited RAM buffer efficiently. You don't want it filled with junk before the interesting event happens.
Makes sense. What about intermittent bugs? Those are the worst.
Ah, yes. For those, the ILA offers capture windows. This effectively divides the trace buffer into multiple segments. When a trigger fires, data fills one segment. Then, the ILA automatically rearms itself, waiting for the trigger condition again. If it fires again, data fills the next segment.
Ah, so you can capture multiple occurrences of the bug.
Exactly. It allows you to view multiple distinct trigger events side by side in the waveform viewer. Invaluable for identifying patterns or variations in those elusive, intermittent failures.
That sounds incredibly useful. What if the trigger condition itself is really complicated, like it depends on a sequence of events?
For that, you need to move beyond simple Boolean logic. The ILA has an advanced trigger mode. In this mode, the trigger condition isn't just a simple equation. It's defined by a custom, user-programmed state machine. You write the state machine in a simple text file with a .tsm extension.
A state machine trigger. Can you give an example?
Sure. Imagine you want to capture a complete AXI read transaction, which involves multiple phases over several clock cycles. Your trigger state machine might have states like wait for valid, address valid, then transition to wait for ready, read data ready, then wait for last beat, read data. Only when that whole sequence completes does the trigger fire.
Wow, so you can define complex sequences.
Precisely. This sequence-aware triggering is absolutely crucial for tackling protocol-level issues where a single snapshot in time won't tell you the whole story.
That advanced trigger mode sounds like it could save days of just scrolling through waveforms, hoping to spot something.
It really can. It's a powerful technique.
But what about that hardware-software boundary problem in SOX? Can Chipscope help bridge that gap when a bug involves both domains?
Yes, and this is another critical capability. Vivado provides powerful hardware-software cross-triggering.
Cross-triggering, how does that work?
Two ways. First, output triggering, which is software triggering hardware. You can set a breakpoint in your software code running on, say, an ARM processor in a Zynq or Versal device. When that breakpoint is hit, the debugger can automatically send a trigger signal out to the ILA running in the programmable logic.
Ah, so you capture the hardware state at the exact moment the software hits a certain point.
Exactly. Perfect for seeing what the hardware was doing when the software did something specific.
And the other way?
The other way is input triggering, hardware triggering software. An ILA trigger event in the hardware, maybe a hardware error flag goes high, can be configured to halt the processor.
So the hardware problem stops the software.
Yes. It lets software engineers immediately examine the program, state registers, memory, the call stack, at the exact moment the hardware failure occurred.
That sounds like a game changer for finding those really nasty multi-domain bugs.
It truly is. It provides that essential correlated view.
Okay, so you've used advanced triggering, maybe cross-triggering, and you've captured the data. Now you're staring at waveforms in the Vivado Hardware Manager. What helps you make sense of it all?
The Hardware Manager GUI has several key features for analysis. Perhaps the single most powerful one is cross-probing.
Cross-probing?
Yeah, it creates this dynamic link between the captured waveform data and your actual design source files. If you see an interesting transition or value on a signal in the waveform viewer, you can just right-click on it. And Vivado will instantly navigate you to the corresponding net in the synthesized netlist view, show you its physical location in the device view, and most importantly, jump you directly to the line of Verilog or VHDL source code where that signal was originally defined.
Whoa. From waveform glitch straight back to the source code line.
Exactly. It's a massive productivity enhancer. It bridges the gap between the symptom you observe in the waveform and the potential cause in your code instantly.
I can see how that would save huge amounts of time.
Definitely. Then specifically for AXI interfaces, remember the system ILA. Its protocol-level debug capability is key. The waveform viewer doesn't just show raw bits for AXI signals. It interprets them as complete AXI transactions, displaying them as composite objects showing address, data, response codes, timing information.
So you see reads and writes, not just signals wiggling.
Right. It even performs some basic AXI protocol checking for violations. It lets you debug at a much higher level of abstraction, focusing on the transaction flow.
That's much more intuitive for bus debugging.
Absolutely. And finally, don't forget that the captured data isn't trapped inside the Vivado GUI. For custom analysis, you can export it. You can save waveforms to a .wcfg file to reopen in Vivado later, or export to a standard .vcd value change dump file for use in third-party waveform viewers or analysis tools.
Okay, standard formats.
And going back to Chipscope, the Python API lets you read the captured trace data directly into a Python environment.
Right, unlocking NumPy, Matplotlib.
Exactly. This opens the door to limitless custom analysis. You can write Python scripts to calculate AXI transaction latencies automatically, perform FFTs on captured ADC data, compare captured results against a golden reference model, whatever you can imagine coding in Python.
This evolution in analysis, it really highlights a profound shift, doesn't it? Hardware debugging isn't just looking at signals anymore. It's becoming a sophisticated data analysis problem in its own right.
That's a perfect way to put it. The tools and techniques are increasingly about extracting insights from complex data.
Now, while all this on-chip debug capability sounds indispensable, you hinted earlier that it comes with a cost. This idea of the observer effect. The debug logic itself consuming resources and potentially impacting performance. That sounds like a genuine paradox. Has there ever been a time, maybe in your experience, where the debug logic itself introduced a new bug or maybe inadvertently masked the one you were actually chasing?
Oh, absolutely. It's a very real and common challenge. Achieving timing closure with Chipscope integrated. You can have a design that meets all its timing constraints perfectly on its own.
Right, passes timing clean.
And then you insert an ILA or VIO core, run implementation again, and suddenly you have timing violations popping up all over the place.
Ouch. So what causes that? Why does adding debug logic break timing?
Several root causes. One is simple resource congestion. The debug cores themselves consume lookup tables, LUTs, and flip-flops, FFs. But more significantly, their probe connections often need extensive routing across the chip fabric. This extra routing can create localized congestion, forcing the place and route tools to use longer, less optimal paths for both the debug signals and nearby functional logic.
Crowding things out.
Exactly. Another factor is increased fan-out. When you tap into a signal to probe it with an ILA, you're adding an additional load onto the net driving that signal. This increases its fan-out, which increases the net delay, potentially causing setup time violations on paths that were previously okay.
Right, more things listening slows it down.
Yep. And finally, there's placement disruption. The physical logic cells making up the debug core have to go somewhere. Sometimes they displace functional logic that was sitting in an optimal location on a critical timing path. Forcing that functional logic to move somewhere else lengthens delays.
So it's a constant balancing act between visibility and performance.
It absolutely is. You need the visibility, but you can't break the design to get it.
So how do engineers manage this? What are the strategies to mitigate these timing problems?
There are several key strategies. Ideally, you design for debug, right from the start. If you know certain modules are complex or high frequency and likely to need debugging, you plan for it, maybe budget some resource overhead in those areas early on.
Proactive planning.
Yes. Having robust timing constraints in your XDC files is also crucial. Well-constrained designs are generally more resilient to the perturbations caused by adding debug logic.
Good constraints help the tools cope.
They do. And then leveraging those iterative and guided implementation flows is key. The best practice is usually to get your functional design timing closed first without any debug cores.
Get the core design working.
Right. Then, use Vivado's incremental compile flow to add the debug cores. This flow, remember, tries hard to preserve the existing placement and routing of the functional logic, minimizing disruption.
Okay, add debug gently.
Exactly. You can also use strategic placement. Using placement constraints like P-blocks in Vivado, you can guide the placer to put the debug cores in less congested areas of the chip, physically separating them from known critical timing paths.
Manually guide the tools.
Sometimes necessary, and critically, perhaps the simplest thing. Minimize the debug footprint. Only probe the signals you absolutely need for the current problem. Every single additional probe adds routing burden and increases risk. Be selective.
Don't just probe everything just in case.
Please don't. It's tempting, but it often causes more problems than it solves.
How do you actually know how much resource cost you're adding? Can you estimate it?
Yes, and that's really important for planning. You quantify the cost by looking at the resource utilization estimates. This is measured primarily by the consumption of FPGA logic resources, LUTs and FFs, and memory resources, specifically the block RAMs used for the trace buffers. The main factors influencing the cost are the number of probe ports you enable on the ILA, the width of each probe port, how many bits, the selected data depth, which dictates BRAM usage, and sometimes the complexity of the trigger mode configured. Vivado provides really invaluable tables in its documentation, for instance, showing the typical resource utilization for different ILA configurations on specific device families like Kintex 7 or Vertex Ultrascale.
Ah, so you can look it up beforehand.
Exactly. These tables let engineers estimate or quantify the cost of a proposed debug strategy before committing to what could be a long implementation run. It enables proactive, evidence-based decisions about your debug setup.
So, in essence, it really means being smart, being strategic about your debug setup, treating the debug configuration almost as part of the overall design challenge itself, not just an afterthought.
Precisely. It requires a thoughtful approach.
And does this strategic thinking change much when you're dealing with really complex architectures, like those heterogeneous SoCs or designs using partial reconfiguration?
It does require adapting the strategy. For heterogeneous SoCs like Zinc and Versal, you really need that holistic view we talked about. Debugging often involves interactions between the processor system PS and the programmable logic PL. So techniques like AXI bus monitoring using the system ILA and that hardware-software cross-triggering become absolutely critical. For Versal specifically, with its AI engines and network on chip, the AXI-based debug fabric provides the necessary infrastructure to get visibility across all these different domains.
Right, the unified fabric helps.
And for designs using dynamic function exchange, DFX, formerly known as partial reconfiguration, debug cores can reside either in the static, unchanging part of the design or within the reconfigurable partitions themselves. Debugging across those static or configurable boundaries can be tricky, but again, especially for Versal DFX designs, the move to AXI-based debug helps simplify the connectivity and communication with debug cores, regardless of where they are physically located.
It's clear Chipscope is a really powerful, comprehensive solution from AMD Links, but, it's not the only game in town. How does it stack up against the competition? And looking forward, what does the future hold for on-chip debugging, given that hardware just keeps getting more complex?
That's right. The primary alternative, especially in the Intel FPGA world, is their on-chip debug solution, centered around the Signal Tap 2 logic analyzer.
Signal Tap? Okay. How do they compare?
At the core functionality level, they're aiming to solve the exact same problem, and honestly, they offer largely equivalent capabilities. Both involve instrumenting the design with soft-core analyzers. Both capture data synchronously into on-chip memory. Both have configurable triggers.
So feature parity, mostly.
For the core features, yes. Both offer multiple ways to insert the debug logic, similar to the flows we discussed for Vivado. Both have advanced features like segmented buffers for capturing multiple events. SignalTap calls it segmented buffer. Vivado ILA calls it capture windows. But it's the same concept.
Okay, so where do the differences lie? Is it user experience?
It's performance. That's where things get more subjective. And you'll hear different opinions from engineers. Some users report that Vivado ILA's waveform viewer, especially when dealing with really large trace buffers, can sometimes feel a bit slower or less responsive to refresh compared to SignalTap.
Interesting.
Conversely, other engineers really praise the Vivado ILA workflow and the logic of its GUI, sometimes saying it feels leaps and bounds better, particularly mentioning flexibility in how you can modify the waveform display after capture without having to change the core configuration itself. Also, the overall toolchain integration Vivado plus the Vitis software platform is often perceived by users as perhaps more tightly unified than the Intel Quartus plus platform designer environment.
So if we connect this to the bigger picture, the choice often comes down to maybe what ecosystem you're already in, developer familiarity, specific workflow needs.
And honestly, sometimes just the subjective feel of the tool that an engineer prefers. Neither is definitively superior across the board. They both get the job done effectively.
Right. Okay, so that's the present landscape. What about the future? Where is on-chip debug heading?
The future trajectory is really exciting, and it's being driven hard by that relentless increase in design complexity, the rise of heterogeneous computing platforms like Versal, and also the increasing adoption of software engineering methodologies in the hardware world.
Okay, what are the big trends?
I see 4 major trends emerging. Trend 1, AI and machine learning-assisted debugging.
AI for debugging. How would that work?
Well, the sheer volume of data generated by modern designs, especially in simulation logs and trace captures, is becoming overwhelming for humans to sift through manually. ML algorithms are really good at pattern recognition and anomaly detection. So future tools could use ML to analyze signal traces, system logs, maybe even historical bug reports, to automatically identify suspicious patterns or anomalies that a human might miss. They might offer ranked lists of potential root causes or even provide guided debugging workflows, acting like an intelligent assistant.
Like an AI co-pilot for debugging.
Interesting. It's exactly. Trend 2, truly unified hardware-software code debugging. We talked about cross-triggering, which is a step in this direction. But the line between hardware and software in SOCs is getting blurrier and blurrier. Future tools need to provide deeply integrated, synchronized, time-correlated views of both domains simultaneously and seamlessly. Imagine setting a breakpoint in your C++ code and instantly seeing the exact corresponding hardware state changes in the waveform viewer perfectly aligned in time, and vice versa. It's about a seamless, holistic system view.
That would be amazing for SOD developers.
It's essential. Trend 3, debugging in the cloud and distributed systems. We're seeing more and more FPGAs deployed in cloud data centers. This makes remote debugging the absolute norm, heavily relying on those virtual JTAG or AXI over IP technologies like XVC. Cloud infrastructure also enables new possibilities, like massive parallel simulation or hardware testing and automated fault injection campaigns running across hundreds or thousands of FPGAs. And for systems built from multiple FPGAs working together, distributed systems will likely see new techniques emerge, maybe embedding time-stamped error detection logic, like CRC checkers or watchdog timers, all synchronized to a common network time source, allowing engineers to reconstruct a global view of failures across an entire farm of devices.
Wow, debugging at data center scale.
It's coming. And trend 4, abstraction for high-level synthesis, HLS. More and more hardware design is moving to HLS, describing logic in C++, System C, even languages like Python using frameworks like PyNQ.
Right, designing hardware like software.
Exactly. But today, debugging HLS designs often means dropping down and looking at the auto-generated, sometimes cryptic, RTL code. Future debug tools must operate at the same level of abstraction as the design entry. That means being able to probe variables, set breakpoints, and analyze behavior directly within the original high-level C++ or Python source code, with the tool automatically handling the mapping down to the underlying generated hardware signals and structures.
So debug matches the design abstraction level.
It has to. No more digging through generated Verilog when you wrote the design in Python.
It really sounds like the future of hardware debugging is about pushing for more intelligence, deeper integration across domains, and higher levels of abstraction, all aimed at making it more accessible, more efficient, and maybe, just maybe, a little less frustrating.
That's the goal. And based on these trends, we can distill some best practices for engineers using tools like Chipscope today.
Okay, let's hear them. How do you debug like a pro?
First, and this is crucial, embrace a hybrid verification strategy. The golden rule is simple. Find and fix as many bugs as you possibly can in simulation first.
Do the easy stuff in sim.
Exactly. Visibility is perfect there. Iteration cycles are much faster. Use Chipscope and on-chip debug for validation. Reserve it for those hard problems that only show up in a real system environment. Things involving external interfaces, subtle real-world timing, performance bottlenecks, those elusive hardware-software interaction bugs.
Use the right tool for the right phase. Makes sense.
Second, plan for debug from day one. Don't treat it as an afterthought. When you're architecting your design, identify the complex or high-risk modules early on and proactively think about what debug capabilities you might need there. And as we discussed, budget for the overhead. Acknowledge that debug cores consume resources, LUTs, FS BRAMs. Factor that overhead into your resource estimates early in the design cycle to avoid hitting constraints later when you desperately need to add debug.
Don't paint yourself into a resource corner.
Right. Third, adopt a script-based, reproducible workflow. We talked about TCL and Chipscope. Use them. Script the entire debug instrumentation process, adding cores, connecting probes, setting parameters, and absolutely version control your debug setup. Treat your TCL or Python debug scripts just like source code. Store them in Git or your version control system. This ensures your debug setup is reproducible, trackable, and easily shareable with colleagues.
Infrastructure for debugging.
It's essential for efficiency. Fourth, start small and iterate quickly. When you first detect a failure on hardware, resist the urge to probe hundreds of signals immediately. Instead, start by probing a small, targeted set of signals that you hypothesize are most likely related to the failure.
Be focused.
Be focused. Then, leverage those fast iteration flows incremental compile, or the ECO flow if applicable, to rapidly change which signals are probed as you gather more information and narrow down the bug's location. Avoid that temptation to just throw every signal into a giant ILA. It usually just slows down your implementation runs and makes analysis harder.
Iterate intelligently.
Yes. Fifth, master advanced triggering. Don't just stick to simple edge triggers. Invest the time to learn and effectively use the ILA's advanced trigger mode with those custom state machines, the .tsm files.
Embrace the complexity.
Embrace it. For protocol-based bugs or issues in complex state machines, think in terms of sequences. Define the exact sequence of events that constitutes the failure you're seeing. A well-designed trigger state machine can isolate exactly that sequence, saving you potentially hours or days of manual waveform sifting. That's where the real detective work pays off.
Pinpoint the problem precisely.
And finally, remember the ultimate goal. Try to replicate the bug back in simulation. While Chipscope is essential for finding those tough bugs in hardware, the most efficient place to actually fix them is almost always back in simulation.
Find in hardware, fix in sim.
Exactly. Chipscope acts as the bridge. It helps you capture the real-world stimulus and behavior that are likely missing from your original simulation test bench. Use the insights gained from Chipscope, the trigger conditions, the captured sequences to enhance your test bench. Once you can reliably trigger the bug in your simulator, you can leverage the simulator's much better visibility and rapid iteration cycles to implement and thoroughly verify the fix quickly and confidently. This hybrid workflow, find in hardware, fix in simulation, is truly the hallmark of a mature, efficient, and effective verification methodology.
Wow. What an incredibly insightful deep dive into the world of AMD Vivado Chipscope. Seriously, from understanding why the old ways just couldn't keep pace, to exploring this powerful arsenal of ILA, VIO, system ILA, and even peering into that fascinating future of AI-assisted debugging, it's crystal clear that finding those elusive hardware bugs is evolving into an increasingly sophisticated science. It's not just about probes anymore, and the core takeaway from me listening to all this isn't just about the specific tools, but the strategy behind using them effectively. Planning for debug right from the start, truly embracing automation with scripting, mastering those advanced triggers that can really transform what often feels like a frustrating, hair-pulling hunt into, well, maybe an efficient and even enjoyable puzzle to solve.
Hopefully more enjoyable, yes.
So let me leave you, our listeners, with a provocative thought to mull over. As hardware design continues its frankly dizzying ascent into ever greater complexity, will our debug tools always just be playing catch-up? Or are we maybe, just maybe, on the cusp of an era where intelligent automated systems can actually start to anticipate and help us prevent certain classes of bugs before they even manifest in the first place? Something to think about until our next deep dive.